Hello, this is MEI Further Maths Core Pure. We're in the second Sequences and Series section, and on the third video on using induction to prove results about divisibility. You can watch the video straight through, but you will probably find it helpful sometimes to pause the video and try things out for yourself before continuing to watch. Before we look at proving divisibility results by induction, we will just review some simple results and check on the formal details required. Pause the video for a moment while you try proving that these two expressions are divisible by 3. OK, you'll have started by multiplying out the brackets to get 3m squared minus 2m minus 9m plus 6, take away m. And collecting terms, that gives us 3m squared minus 12m plus 6. We can see that this expression is divisible by 3 because each of the terms has a coefficient which is a multiple of 3. And you may have left it there. But if we're doing this formally, you need to do another step. You need to actually take out the factor of 3 to demonstrate that we can divide and be left with a whole number. So there is 3 times an integer, and we can now say which is divisible by 3. For the second one, again, we can see straight away that each term is divisible by 3, but we need to do this formally. We need to be able to take out a factor of 3. So we'll change that 9 to a 3 squared. Tidy up the index to get 3 to the power 2m plus 2. And now we can take out a factor of 3. That leaves 3 to the 2m plus 1. Take away 1. And again we need to write down which is divisible by 3. OK, let's look at an example of proving divisibility by induction. Here we're asked to prove that this expression is divisible by 8 when n is a positive integer. Remember the 3 steps for a proof by induction. Check it's true for the first one, which in this case is n equals 1. Then show that if the result is true for a particular number n equals k, then it's also true for the next one, k plus 1. And then write our conclusion clearly. OK, we'll start with step 1. If n equals 1, then we have 7 to the 2 times 1 minus 1 plus 3 to the 2 times 1, which is 7 to the 1 plus 3 squared, which is 7 plus 9, which is 16, which is divisible by 8. Note that when we're dealing with a particular number, we don't need to show that it's equal to 8 times 2 if it's obviously a multiple of 8. Then we need to assume that the result is true for n equals k. And we should write down what that assumption means. In this case, we're saying that 7 to the 2k minus 1 plus 3 to the 2k is equal to 8p for some positive integer p. And now we need to consider the case where n equals k plus 1. We now have the expression 7 to the 2k plus 1 minus 1 plus 3 to the 2k plus 1, and we need to show that this is divisible by 8. We can use the assumption from the previous slide that 7 to the 2k minus 1 plus 3 to the 2k is equal to 8p for some positive integer p. So we need to transform this expression into something which enables us to use the previous example. I want to make this first term look like this term here, and it's 7 squared times too many. So I'm going to take out a factor of 7 squared, leaving me with 7 to the 2k minus 1. Let's just check. That makes 7 to the 2k plus 1, and here I've got 7 to the 2k plus 2 minus 1, which is the same. I need the whole of this term here to make sure I've got a multiple of 8, so I'm just going to write in plus 3 to the 2k. Now I need to make what I've got here equal to the line above, so I'm going to remove that extra bit that I added, which is 7 squared times 3 to the 2k, and I'm going to add on the bit which I want, which is 3 to the 2k plus 1. All I need to do now is show that this is equal to a multiple of 8. So the first part, because I carefully constructed it to be so, is 7 squared times the previous expression, which we know is equal to 8p. Over here I've got rather a mess, but I can see that I've got a lot of multiples of 3 in both terms. So I'm going to take out a factor of 3 to the 2k, just because it seems to be the only sensible thing to do. My first term is then 7 squared, and then I need to subtract because I've got a minus at the beginning there. And here I've got 3 to the 2k plus 2 if I multiply that out. So I've got a 3 squared there. Now let's see what this looks like. Well, 7 squared is 49, and 3 squared is 9, and 49 take away 9 is 40, which very conveniently is a multiple of 8. Now I can take out a factor of 8 from the whole expression, leaving me with 7 squared p minus 3 to the 2k times 5, which is divisible by 8. Now I can write my conclusion. So if the result is true for n equals k, then it's also true for n equals k plus 1. As the result is also true when n equals 1, it must be true for all natural numbers n greater than or equal to 1 by mathematical induction. There are more notes on integral on using induction to prove results about divisibility. That's the end of this short video. The next video in the series is on using induction to prove results about series.